Next, we are going to talk about what is band theory. Band theory helps us to understand why conductors such as metals can conduct electricity very easily, whereas insulators are almost impossible to conduct electricity, and why semiconductors sometimes can also conduct electricity. So, what do they say in band theory? Is imagine in an atom, you have the nucleus with all the electrons orbiting it. Now, let's say the electrons at the outermost shell, we will call that as the valence electrons. So, in a metal, you already have a few valence electrons. And remember that when we also learn this in chemistry, we know that there are many empty places within the outer shell. All right, and we will talk about that later. But let's talk about these valence electrons. So these valence electrons will have their own energy. In other words, you can assume that it has its Ke due to its motion, as well as the Pe due to the attraction with the positive nucleus. And if there are other atoms nearby, because in an atom you have many of these atoms nearby, and each of these electrons which are orbiting the nucleus are also the valence electrons. So each of these valence electrons will have their own energy level, meaning to say there's a specific value of Ke plus Pe, so together it's called the energy level. So what we will do is we will plot all the energy levels of these valence electrons and call it the valence band. Now, if you have many of these electrons, the energies will be very similar to each other. So if you draw many of them together, it will seem like they form a continuous band. So this continuous band is what we call as the valence band. But don't forget that in a metal, you also have all these empty places within the same shell, which are empty, and so that all these valence electrons can easily move into. Now, each of these places which are empty have also an associated energy level, meaning to say if the electron goes to here or here in the empty one of the empty slots, it will have a specific value of Ke and Pe, so that would form the energy of the what we call as the conduction band. So if I were to plot the energies of these empty places where the electrons could go to, I will get again many of these energy levels, because in each of these atom there are so many empty spaces. So each of these empty spaces, the energy levels are what I'm plotting here. So this is what we will get as the energy levels which are continuous. All right, it seems continuous, and they seem to overlap with the original valence band, because all these electrons in these empty spaces, because they are within the same shell, their energies will also be very similar. So all these energy levels of these empty places that the electrons could go through, which we plotted all these energy levels, we'll call it as the conduction band. All right, so you will notice that in a metal, part of the valence band overlaps with the conduction band. You can also see it here. Part of the valence band overlaps with the conduction band. And because they are overlapping, that means the electrons which are initially at the valence bands, this energy level, they can easily move over to any of these empty places, because it is just a continuous energy level and the energy levels are very similar. So you just apply a potential difference across the metal. That means you're giving it a bit of energy. They will actually easily move into the empty spaces. So when they start to move along the empty spaces, that is when we say that electrons are flowing. So that gives us the current. So this is why for a conductor, the electrons are able to conduct electricity easily, because it's easy to move over to the conduction band. But in a semiconductor, the difference between the valence band and conduction band is there is a gap in between. That means why? Because in a semiconductor or even an insulator, the valence band is completely full. That means for the atom, the outermost shell is completely full. There are no more vacancies. So all the valence electrons are in their outermost shell, and there are no vacancies. And the electrons at this valence band also have their own energy levels. But the problem is they have no space to move to, which is why they can't conduct electricity unless you give some of the electrons enough energy to jump to the conduction band. So what is a conduction band? So the conduction band you can assume to be another set of energy levels in the next outer shell, because this current outer shell is completely full, so you have to go to the next outer shell. And for a semiconductor, if you manage to give some of the electrons enough energy to jump to this new outer shell, there'll be a lot of vacancies there, so they can start to move around when you apply a PD. So which is why if you give them sufficient energy, they can conduct electricity. For example, in a thermistor, you could give the energy in the form of heat, because when you raise the temperature, the electrons gain the energy from the heat, and they will jump to a higher conduction band, so they can start to conduct electricity. In an LDR, you can supply the energy by way of light, because the light means they contain photons. So when the electrons gain the energy from the photons, they can also jump up to a higher energy level, which is your conduction band, which is also your next outer shell. So once they are there, there'll be many empty spaces for them to move when you apply a PD, so therefore they can conduct electricity. But in an insulator, this gap between the valence and the conduction bands this gap is too big. So it is almost impossible for you to supply the electrons with enough energy to jump over. So since these valence electrons are completely full, they have no more space to move about, so therefore they cannot conduct electricity. All right. You can imagine the case, for example, you can use a classroom as an example. Imagine in a classroom, there are all these chairs here, and in a classroom, some of these chairs are already occupied. So, but there are also many empty chairs there within the classroom. So it is actually quite easy for you to ask any of the students to move over to any of these empty chairs. So this is the condition like a conductor. So you have many of these valence electrons, but you have also many of the places which are empty. So it's easy for you to make the electrons travel along the conductor, because there's already empty spaces within the same outer shell. Whereas if we're talking about semiconductors, you could imagine that all these seats are already full. All right, in a semiconductor as well as an insulator, all the seats in the classroom is already full. So if you want the students to move about, you will have to find another place, maybe another classroom. So for a case of a semiconductor, it could be another classroom in the next within the same floor, right? But maybe just next door. So therefore, for these electrons, you can imagine there's another class next door which have all these empty seats, just waiting for the electrons to come over. So if you could give the electrons sufficient energy, or in this case, if you could sufficiently motivate your students to actually want to switch classrooms, which is pretty difficult, harder than them to switch spaces within the classroom. But if you could give them sufficient energy, they will move forward. If they move forward, they can start to move around, because there'll be a lot of empty spaces. But in insulator, you can imagine this empty classroom with a lot of empty seats to maybe be another classroom 3 or 4 levels higher. So you know the students will be too lazy to climb up the stairs, so it'll be impossible for you to ask them to actually want to go up there. Or you can even imagine an even more impossible case. Maybe all these classrooms, maybe all these seats in this classroom is in another college or another school. So for you to ask them to move to another school, that would be like almost impossible. All right. So therefore it is difficult for any electrons to actually move forward. So therefore, in an insulator, they cannot conduct electricity. So another thing that we need to know is that this gap here, which is called the band gap, all right, will be the biggest for the insulator, then followed by a semiconductor. But in a conductor, there's no band gap. Now, another thing that you also need to know is the effect of temperature on semiconductors and on conductors. For semiconductors, when we raise the temperature, you will actually be giving the electrons more energy to jump into the conduction band. So the higher the temperature, the lower the resistance, or the higher the conductance. But for a metal, when you raise the temperature, you are not going to increase the number of electrons jumping over to the conduction band, because the electrons in the conduction band actually come from the valence band, which is already the maximum number of electrons you can have. Which means to say, if you were to raise the temperature, you will not be making more electrons jump into the conduction band, because all the electrons in the conduction band actually already come from your valence band. It's already easy for them to move about, so you don't get any extra electrons there. But what will happen is the atoms will vibrate faster when temperature increases. So when the electrons try to flow through the metal, which is the solid, it will encounter more collisions with the atoms, which will actually slow down the electrons. So when the rate of flow of electrons slows down, your current decreases, and we say that the resistance increases. So you will understand why temperature actually has an adverse effect on conductors, but it's a good effect on a semiconductor.